welcome back. This is lesson 70. We're still Monday, and it's still a rainy, cloudy Monday. Lesson 70, page 464. This is talking about pyramids. Remember pyramids? I have a pyramid here. It's a pointy shape. This is a regular pyramid. This is one of the Platonic solids, one of the five, so it has all congruent triangles. Bottom here, 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 and here. They're all four congruent. Pyramids don't have to be like this. They can have any shape on the bottom. Remember, they could have any polygon on the bottom. And as long as all the sides are congruent triangles, then it is still a regular pyramid. So for instance, this bottom could be a square. And that's actually how the great pyramids of Egypt are. The bottom is a square, and there'd be four triangles, but they're all four congruent to each other. You could have a hexagon on the bottom. You could have a pentagon. Again, that'd be a pentagonal pyramid or a hexagonal pyramid, whatever. Bottom is a polygon of some type, and the sides are congruent triangles. That is a regular pyramid, and that's what we'll be talking about. The top of the pyramid is called the vertex. Vertex of the pyramid in this case is the top one. These are not vertexes, even though we sort of would think of them as that. It's the common vertex of the lateral faces. So all these are lateral faces, remember that? And then the common vertex, all the lateral faces share one point at the top. That's the vertex. The base is the bottom, of course. It's the one that's opposite the vertex. So you just pick that and you say, okay, here's the vertex. That means this is the base. Usually think of it as the bottom in this case. Again, a regular pyramid is a pyramid with a regular polygon as the bottom and lateral faces that are congruent isosceles triangles. That tells you, the isosceles part tells you that the point is directly over the center of the bottom, of the base. In that case, that makes this side and this side congruent. That's why they're called isosceles triangles. One term that we need yet is the slant height. The slant height of a regular pyramid is the distance from the vertex of a regular pyramid to the midpoint of the bottom of one of the edges. So it's not just the height like this, it's the slant height, which would be tilted like this. So it's a line, if you can see that, it's a line that goes from this point to the midpoint here. It'd be drawn right on here. I don't have it drawn, but it would be this line. If I would draw a line right there on the face, that's the slant height, and it would be slanted if you look at it. All right. Finding the lateral area of a regular pyramid, there's a formula for it. You don't really need to memorize the formula in my case, in my opinion. The lateral area of a regular pyramid is simply the area of this plus the area of this plus the area of this. If it's a regular pyramid, all these triangles are congruent to each other. So you would say that I need to know the bottom here. I need to know this, which if you tilt it up, it just becomes a triangle. And this is the base, and then I need to know the height up here. Well, if you put it in a pyramid, then this is the bottom of a base, and this is the slant height. So it's still this. Now you could say it's this times 1/2. Then it's also times however many pyramids you have. The formula says 1/2 perimeter times slant height. And if you think about it, this is the perimeter here plus this plus this. That's really taking the three triangles that you have. So it's the base plus the base of this one plus the base of this one. That's the perimeter. So it's perimeter times slant height times 1/2. That's the same formula as finding them individually, but that's all one formula. So the lateral, again, not the bottom, but just the lateral surface area of a regular pyramid can be found with the formula 1/2 perimeter times slant height. And then, of course, the surface area, this is the next page, top of 465. And this one, you really don't need to know this formula, but the formula for the surface area of a pyramid says that the total surface area, they call it S, big S, of a pyramid is given by the formula below, where big L is a lateral surface area and big B is the area of the base. So the surface area of a pyramid, they say find the lateral area and add the base to it, which is pretty easy to say. Look at example 2 in your book. Everyone look at example 2. That's page 465. We're on lesson 70. Example 2, calculating surface area of a pyramid. And you'll have problems like this in your homework. You also will have them probably later on in life in the form of a test. Calculate the total surface area of a regular hexagonal pyramid with a slant height of 12 and a base side that is 3 centimeters long. Now, this is not a hexagonal pyramid. This is the bottom is a triangle. But a hexagonal pyramid has a bottom hexagon on the bottom, and then triangles going up from there. So the only thing they tell you, I'm not going to draw it in 3D, but the bottom would be a hexagon, which is 6, looks like this, and has a bottom base side that's 3. So this is 3, and then the whole thing is the slant height that is 12. All right, first thing let's do is try to figure out this bottom base. And we had a problem like this before. This is a hexagon, and it's a regular hexagon because it says a regular hexagonal pyramid. That means these all are congruent, so we could just write 3, 3, 3 all along here. That's good, but the perimeter doesn't really help us find the area of this. What we need to do is find the center, divide it into triangles, and this becomes a line that we talked about. It's a special name. Remember, apothem or apothem, depends which persuasion you are. Apothem versus apothem. I'm going to say apothem. We need to find this distance, and to do it, it looks a little bit incomplete, like we don't know what this is. But let's take this triangle out, and in fact, let's just take this half triangle out of this drawing and simplify it a little bit. Here we have it. This was 3 out here. We know this is a regular, so it goes to the middle. We know that this is half of 3, so 1.5. Since this is a hexagon, you could do the math, but these are all bad drawing, but these are all equilateral triangles. So here's one, here's one, here's one. That means these are all 60-degree corners. So this is a 30, 60, 90 triangle. If you remember the side lengths of a 30, 60, 90, this is 90, this is 60, and this is 30. 1, 2, square root of 3. So this is twice this, which makes sense. If this is an equilateral triangle, all the side lengths are 3, 3, 3, and 3. So this is 3 out here. This is 1.5. You could use the Pythagorean theorem to find this. Remember, this is c squared, the hypotenuse over here. Or you can just think of 1, 2, square root of 3. So this side is a square root of 3 times bigger than this. And we had this before. We said it's 1.5 times square root of 3. We don't like a decimal and a square root thing. That looks kind of messy. So let's take everything times 2 to get rid of this. And it would be 3 square root of 3 divided by 2, which is the same as this. So 3 square root 3 divided by 2. This is the same as that. Now it looks maybe more clunky because you got a fraction and all that, but it's a neater way of looking at it. It gets rid of the decimal. And that is the way that they find the apothem. So that is, again, that's this distance right here, which is the apothem right here. That will help us find the area of this. And you can use this then and say, okay, just do your triangles, find the area. Then it's 1.5 times square root of 3 is this, times your base, times 1/2 times 6, or use the formula from previous lesson, and that is the area of a base is 1/2 of the apothem times the perimeter. And again, it's the same thing as finding 1 times 6. You're just taking the perimeter, and that takes care of however many triangles you have in here. But that's example 2 there. So now you find the apothem. Use that to find the area of the base carefully, according to the book here. And then once you find the area of the base, then you're going to calculate all these other ones that are coming up. Remember, the initial problem we looked at was can't draw from the try anyway. It's like a thing here in the top, and can't do it. It's too hard to do. But a hexagonal pyramid. So now you got to find the area of all these triangles in here. Now you know the slant height. The slant height is 12. They tell you that, and you know this is 3 down here. And you can go from there. You find the area of the base, and then find the area of these 6 triangles up top. All right, towards the bottom of the page, another term is altitude. So now we know what slant height is. That's the distance that's laying against the surface here, this angled piece. The altitude of a pyramid is simply the height straight up. And so in a regular pyramid like this, it would be you could imagine a string that leaves the middle of the bottom here and goes up to the top. There's this perpendicular distance. It's the height, really. The height of a pyramid, altitude, height, same thing. And that is what you need to know to find the volume. Remember, in a sense, I say whenever you need to find the volume of something, in a way you're looking at the bottom, what's the area of the base, and then fill it up. So it's the area of the base times the height. Well, that's true for straight up stuff like cylinders and boxes and so on. But this pyramid is going to be something different. It's going to be something less than that because these are tapered in, so you're going to get less and less and less volume or water. You can't just find the area of the base and then fill it straight up. So it's a fraction of that. And for a pyramid, It's 1/3. 1/3 is kind of a weird thing. We've never had 1/3 before. We have 1/2 where you talk about the surface area of a triangle, 1/2 of base times height. But because it's in 3 dimensions, 3D, then it becomes 1/3. So the volume, this is simply a formula you need to memorize. The volume of a pyramid is 1/3 of the area of the base times the height. A common error there would be you use the slant height as the height, and that is not going to get you the right thing. So you need to know the perpendicular distance, that's the altitude or the height of the triangle. Height of the triangle times the area of the base times 1/3. And we could prove that if we somehow make a prism that has this shape and is up here, and then we chop it up and try to fit it, and we could fit 3 of these into one prism that has the same bottom here. To have a triangle down here and a triangle up here, and the same height up here, we could fit 3 of these in. And it may not seem intuitive, but that's what it is. So 1/3, a pyramid is 1/3 base times height. And that is all. They make it complicated on page 466, or they try to make it more complicated, like example 4. A certain pyramid there, regular square pyramid. It's the main entrance of a museum in Paris, and I don't know French, so I'm not going to say it. It has an approximate height of 70 feet, and its square base has sides that are 115 feet long. What's the lateral area of the pyramid? Well, they give you dotted lines in there to help you figure that out. And you think of it as a cross section in there. Since it's 115, it's 115 divided by 2. That's the short leg, and then the slant height, and on. You can figure it out. So look through example 4 carefully on lesson 70, and that will help you on the problem, on your homework problems. All right, that is the end of lesson 70. I'm going to give you the homework for lesson 70, and then you can go to work. For lesson 70, the homework is 1, 2, 8, 11, 16, 19, 20, 23, 24, 27, and 30. For lesson 70, 1, 2, 8, 11, 16, 19, 20, 23, 24, 27, and 30. And that is it.